Hello everyone. In the last couple of videos, we came up with new modes of operation, and one of it was velocity saturation region of operation. And we came up with a drain current model that will try to represent all of them. Okay, and the drain current model was called something what you see over here. It's id equal to kn vgt multiplied by vmin minus vmin square by 2 and 1 plus lambda vds. So let's keep it for now, because whenever you go for values which is very low value of lambda vds, this term will automatically get vanished. So let's try to keep this term over here. In the previous videos, we had observed that this was true only for your saturation region, but let's try to keep it for all kinds of operation region of operation, because for lower values of vds this will automatically get vanished. Okay, so let's keep it and move forward. So vmin will represent minimum of vgs minus vt, vds and vd set. So whichever is minimum, we can just substitute that value in place of vmin, and we can get the drain current equation for that particular working operation. Okay, so let's try to do an example over here. So now in this case, vgt is vgs minus vt, as we have already talked about it. And whenever your vgt is 0, there is no drain current, your drain current is 0. So both the cases, the transistor enter into a cutoff region, that is, it's completely off. Okay, so that was drain current, that was the cutoff region operation when your vgs minus vt is less than 0. For the rest, we have these models. Now let's try to look into them one by one. So before entering into that, let me give you one more technology parameter that will be used while we do the spice simulation for short channel, and that's vd set. Okay, so vd set, since the foundries know what values of vd set, at what values of vd set your device will enter into velocity saturation region. So that value will become as a technology parameter, and that comes with your node, with your technology node. So whenever you have a value of vd set, you just open, whenever you have a device which is less than 250 nanometer, you might want to just open the model file and search for vd set, and you will find that vd set is a technology parameter. The voltage is defined for a particular technology node. Okay, so this becomes a constant value, and it is the voltage at which your device velocity saturates. Okay, and it's independent of vgs plus vds. So now let's get back to deriving the drain current equations for each and every region of operation. Okay, so the first one will take for example vgs minus vt is the minimum value. Okay, so when we say vgs minus vt is the minimum value, what do we exactly mean? So first, what we'll do, let's substitute this vgs minus vt in this equation, and then let me try to deduce something out of it. Okay, so let's put over here. So when we put vgt over here, vmin as vgt, this becomes vgt square, which is mentioned over here. This becomes vgt square by 2, which is mentioned over here. And further, when you evaluate this one, it becomes id equal to vgs minus vt the whole square, or vgt square by 2 1 plus lambda vts. And this equation is a very familiar equation while your device is operating in saturation region. Okay, in both the cases. Now a very quick thing to observe over here is, when your vgs minus vt is minimum, what does that actually imply? It implies that your vds is at maximum voltage, your vds is the highest, because that's the point when your vgs minus vt will be the lowest. When I say VGT is minimum of all, so VDS and VD set are at much higher voltage, which means we are talking about the saturation region, and the model proves it for himself. Okay, so whenever the VGT is minimum for this particular model, you substitute VGT in this equation, and you get id equal to vgs minus vt the whole square, or vgt square by 2 1 plus lambda vts. And this is your equation for higher voltage of vds, and that's the saturation region of operation. And that's true for both the channel nodes, for short channel as well as long channel. Okay, next let's put vds is a minimum value. So before entering into the equation, let's try to analyze what happens when vds is minimum. When we say vds is minimum, it's basically the lower values of vds for which we derived the drain current. So the vds value is lower, but there is some value of vds applied. So for smaller values of vds, we have often observed that the device enters into a resistive region of operation, okay, or a linear region of operation. And to prove that, let's try to put this vds value in this drain current equation and see what do we get. Okay, so if vds is minimum value, and we are talking about values which are less than the vd set, Okay, it's a value where the device is still in the range of 0 to 1 volts for a 5 volt region of operation. Okay, in that case, the equation becomes something like this: id equal to kn vgt into vds minus vds square by 2 and 1 plus lambda vds. So anyways, the vds value is so low that this term will automatically get vanished. 1 plus, it's close to 0, so it's almost 1. Okay, so this term will automatically get vanished, and you will be left behind with this particular equation, which is id equal to kn vgs minus vt into vds minus vds square by 2. And this equation reminds us of the resistive region of operation. Okay, and we just explained that for lower values, and in the previous videos also we saw for lower values of vds you often tend to enter into a resistive region of operation, and that's your region where your device operates. Okay, that's about whenever vds is of the minimum value, and we are left with the last one, which is when your vd sat is the minimum value. So in this case, the value vd sat is applicable only for short channel devices which is less than 250 nanometer and so on. Okay, so there is nothing called a saturation or velocity saturation region for long channel. So vd sat definitely, by the name itself, it says us that it will enter into a velocity saturation mode. But let's try to identify or get the equation for it. Okay, so if it will be just a multiplication of vd sat into vgt or vgs minus vt minus vd sat square by 2 plus 1 plus lambda vds. So this becomes your drain current equation for a device operating in the velocity saturation, and this is the one that is being used, or that will be used for all short channel devices working in saturation mode. This is the equation that will be used. There are even more complex models or accurate models that will be used, but this is the one of the basic simplest model that you can use for your device operating in velocity saturation. Okay, so let's try to expand this equation. So yeah, your device enters into velocity saturation, it's just highlighted over here. So let's try to expand this equation. If you expand this equation, kn, we just expanded kn, and you see it's id equal to mu on cox w by l vgt into vd sat minus vd sat square, the complete equation. If you see, it's mentioned over here. So if you ignore the remaining term, if you see this one, mu on cox w by l, it tends to happen that if you keep your w constant, your L, if your W is constant, the L should increase at lower nodes, because whenever your L it's reduced, the complete drain current equation should increase. That's what this particular thing specifies. But that's not true. We'll come to this term whenever we enter into delay calculation for a device. So let's try to keep it for there. But there will be second observation. This brings us to our second observation, which is that your currents at the saturation region. Basically, we are talking about the current at this point. If your peak current at a W by L device of 1.2 micron cross 1.8 micron cross 1.2 micron, if your peak current is 410 microamps, it's microamps. In this case, your device current, your peak current is 210 microamps. There is a typo over here. It's 210 microamps. So if you see, the trend is not maintained. Basically, at lower values of your device, your peak current tends to reduce. And the reason for this is the velocity saturation, and that's why it's an important term. Whenever we move from higher device to lower device, this is a very important term to note, that velocity saturation causes your device to saturate early, and as a result of that, the peak current that you see for the same W by L ratio is different in two different cases. Okay, so with that we conclude the MOSFET discussion of it, and there are some open source websites over here which you can refer to for getting an hands on SPICE. And next, what we'll be doing is we'll be moving to CMOS voltage transfer characteristics. So this is the one which will actually define the delays of your cell. Okay, so basically CMOS is a complementary MOSFET logic. You have a PMOS on top and MOS at bottom. It's a very common logic that we have. But while understanding the CMOS voltage transfer characteristics, it will give you an insight into the delay of a particular cell, and how does the delay is getting derived for one particular cell. So let's try to do the CMOS voltage transfer characteristics from the next video. Thank you.